Welcome to the first lesson in AP Calculus. So you can see this is Unit 1, Topic 1. The topic is called Introducing Calculus, and answering the question, can change occur at an instant? Because calculus really, at its core, is the mathematical study of things that are changing. And so we're talking about how quickly can that change occur. So you've worked with change before in some context in other math classes. For example, you've worked with the concept of average velocity before. So the example it gives here says, if someone drives 700 miles and it takes them 10 hours, what is their average velocity? Well, that's pretty easy to calculate. We're just going to do 700 miles divided by 10 hours. So 700 miles divided by 10 hours, and we get 70 miles per hour. So that now unit of the rate comes from the units of the distance in time that we had, miles per hour. Now right beneath that it says, what assumption could you make about the person's driving? Would you assume that they drove exactly 70 miles an hour the entire 10 hours? Probably not. So the average velocity isn't necessarily the same as the instantaneous velocity, the velocity at any particular instant. So there were probably some times when he was driving faster than 70, sometimes he was driving slower than 70. It just averaged out to 70 miles an hour. So when we're working with calculus, we're going to be much more concerned with that instantaneous rate of change as opposed to the average rate of change. So in example 1, it says, suppose a ball is dropped from the top story of the Burj Khalifa in Dubai, 2,717 feet from the ground. That is the tallest building in the world. We're going to drop a ball from the top story, and we want to know its velocity after 5 seconds. Because its velocity isn't going to be the same the whole way down. Gravity is going to keep pushing it, and so it's actually going to be speeding up as it falls. So it's going to be going faster after 5 seconds than it was after 2 seconds. And then it's going to be going faster after 7 seconds than it was after 5 seconds. So we're trying to find just its instantaneous velocity, the exact instant 5 seconds after it's dropped. How fast is that ball moving? So there's a paragraph here about Galileo conducting experiments by dropping stuff off the Tower of Pisa. The part here that's going to be important to this problem is this function right here. S of t equals 16t squared. Now it tells us right above that, that function tells us the distance the ball has fallen, not its velocity, just the distance it fell. But that's going to be important in calculating the velocity just like it was up here. We need to know the distance that it covered over a period of time in order to calculate its velocity. So let's start with that. Let's figure out how far the ball fell in 5 seconds. So we're going to find S of 5, because 5 is t seconds after the ball is dropped. So we're going to do 16 times 5 squared. 16 times 25 is 400 feet. The ball fell 400 feet in that 5 seconds. So now we know how far it has fallen, but we don't know how fast it's currently falling. In order to compute the instantaneous velocity, we're actually going to use a little bit of a trick. We're going to calculate its average velocity, just like we did up here, but over a really, really, really short period of time. So it's almost like no time at all has passed because it's going to be so short. So let's say we're going to compute the average velocity over the interval from t equals 5 to t equals 5.1. So just in that 1/10 of a second. If we compute the average velocity in that 1/10 of a second, that's going to be pretty close to its actual instantaneous velocity because it's such a short period of time. So just like we did up at the top, we need to know how far the ball fell in that 0.1 second. And then we're going to divide it by the total time, which is 0.1 seconds. So the next thing we need to find is S of 5.1. And so I'm going to use a calculator for that because I don't know 16 times 5.1 squared off the top of my head. So make sure you have a calculator available too. You're going to need it when we get down to this chart in just a second. So my calculator is telling me that comes out to 416.16 feet. So in that 0.1 second, it went from 400 to 416.16. So its distance was 16.16 feet, and it covered that in a time of 0.1 seconds. So if we divide that, that will tell us the average velocity over that really short period of time. That will be at least pretty close to the instantaneous velocity. Well, when you divide by 0.1, you're just going to move the decimal point one spot to the right. So we'll end up with 161.6 feet per second. So that is at least a good estimate of the instantaneous velocity. But the problem's not asking us to estimate here. It wants to know the actual exact instantaneous velocity. And in order to find that, we're going to have to deal with an even smaller interval of time. That 0.1 second is actually too big. So that's where this chart comes in. We're going to look at even smaller and smaller intervals of time. So we did 5.1 seconds. Let's try 5.01 seconds. And then 5.001, and then 5.0001. And I mean, theoretically, we could go even smaller than that, but we'll kind of see the bigger picture when we do those three. So just like we did up here, the first thing we're going to do is find s of t. So plug it into the function. We'll do 16 times 5.01 squared, and that will come out to 401.6016. So that's a difference. Notice I'm doing here, I'm subtracting that from s of 5, which was 400. So just to find the difference of how far it fell in that additional little bit of time, that's a difference of 1.6016. And the change in time from that to 5 seconds was 0.01. So that's going to move my decimal point twice and give me 160.16 feet per second. So you'll notice it's a similar answer, but not quite exactly the same as the one we got up here. So when we went on that little bit shorter interval of time, we got a different average velocity. Close, but a little probably more precise. So go ahead and pause the video, try to fill in the next two rows of this table on your own and see if you can determine what you think the actual instantaneous velocity is. So pause the video, fill that in, and then press play again and we'll discuss it. All right, so hopefully you've had a chance to fill in the rest of the table here. I'll just get caught up. So at 5.001, s of t should be 400.160016. And at 5.0001, it should be 400.0016. So those are my s of t to find the instantaneous velocity. Here I'm getting 160.016. And then here I'm actually just getting 160.0. And there's probably some stuff back there, but it's too far back that it's not showing up yet. So what we're going to kind of look for is the trend in these velocities. So when we went with a 0.1 second difference, it was 161.6. 0.01, it was 160.16, then 160.016, then 160.0. But you could probably see what we're trending towards. And if I did an even smaller one, 5.000001, then it would probably be like 160.000001 or something like that. But as our interval of time gets smaller and smaller, we can kind of see what the limit of the velocity is. It going down a little bit still, but it's kind of leveling off at about 160. So I would answer that the instantaneous velocity at t equals 6 is, or sorry, t equals 5, is 160 feet per second. So we're just looking over smaller and smaller intervals of time, still finding an average rate of change. But as that interval of time gets small enough, the average rate of change can actually become an instantaneous rate of change. So let's flip over to the next page and look at a sample free response question from the 2018 AP exam. And this is just part of a free response question. Usually the free response questions will have parts like A, B, C, D, sometimes even E or F. Sorry about that. This is just part A of a free response question. So it says the height of a tree at time t is given by a twice differentiable function. Don't worry too much about what that twice differentiable means. We'll get into that a little bit later in the year. The height of the tree is given by the function h, where h of t is measured in meters, t is in years. Selected values of h of t are given in the table above. The question is asking us to use the data in the table to estimate h prime of 6. That's another notation we'll get pretty familiar with this year, but for now, just know that it means the instantaneous rate of change, which I usually abbreviate IROC. So if we're talking about an average rate of change, it would be AROC. It's asking for the instantaneous rate of change at t equals 6. So find out exactly how fast the height of the tree is changing 6 years after it was planted. So in this case, we can't really do that strategy of trying at 6 and 6.1 and 6.01 and so on because we don't actually know the function. We're pretty limited in what information we're given. So if we can't get super precise like that, we're not actually going to be able to compute the instantaneous rate of change, but we don't need to. The problem asked us to estimate. So our strategy is going to be use the smallest available average rate of change over the shortest period of time. So use the smallest available average rate of change. So how close can we get to 6? Well, that's probably going to be looking here between years 5 and year 7 because t equals 6 would be right in between. So if we can find the average rate of change from year 5 to year 7, that will at least give us an estimate of the instantaneous rate of change at year 6. So let's go ahead and calculate that. The change in height over those 2 years was 11 minus 6, so 5 meters, where are units here? 5 meters, and the change in time was 7 minus 5, so over 2 years. So that comes out to 2.5 meters per year is the rate that the height of the tree is changing. Now, that almost answers the question. That answers part of it, but the second part here is really important. Using correct units, interpret the meaning of your answer in the context of the problem. The AP exam likes to give questions like this, where not only is doing the calculation enough, you have to kind of write a sentence explaining what your answer means. So let's do that last part here. So at the time, t equals 6, because we want to be specific, because this rate of change is instantaneous. It's at one specific instant. So at t equals 6, the tree is, well, if its height is changing 2.5 meters per year, you can see from the table it's getting bigger as it goes. So I would say the tree is growing at a rate of 2.5 meters per year. So now we have given correct units. We've interpreted the meaning of this answer in the context of this problem. We told exactly what that 2.5 means. At t equals 6, the tree is growing at a rate of 2.5 meters per year. So that's it for lesson 1. We're just talking about the difference between an average rate of change and an instantaneous rate of change. Like I said in the live meeting, you can check out this table down here if you want a little bit more information about things we'll be looking at in calculus this year. But for lesson 1, that's pretty much all we got. Let me know if you have any questions, and I'll see you tomorrow.